Hello and welcome to Power System Analysis 2. We'll be talking about optimum generator scheduling in this module 3.6. Now, optimal generation and scheduling. We have seen the optimal unit commitment procedures, but there the transmission losses were neglected. We just cannot neglect transmission losses because it is there and you need to consider them. You cannot avoid those transmission losses. So I just read out a paragraph from the book. The modern electric utility serves over a vast area of relatively low load density. The transmission losses may vary from 5 to 15% of the total load, and therefore it is essential to account for the losses while developing an economic load dispatch policy. It is obvious that when losses are present, we can no longer use a simple equal incremental cost criterion. What is this equal incremental cost criterion? It is that lambda. Okay. So if you remember that is the equal incremental cost criterion. That is, the incremental cost should be same, and then it will be equal to lambda. To illustrate the point, consider two bus systems with identical generators at each bus. That is, they have same incremental cost curves. Assume that the load is located near plant 1 and plant 2 has to deliver power via a lossy line. Okay. Now we have to need. So again I am repeating, to illustrate the point, consider two bus system with identical generators at each bus. Okay, so we have two buses and both buses have identical same generator, that is the generators with the same IC curve or incremental cost curves. Now we have to assume that the load is located near plant 1 and plant 2 has to deliver power via lossy line. So load is actually closer to plant 1. For plant 1 there is no loss providing the load, but plant 2 has to pass the supply through a lossy line, that is the transmission line where there is a lot of losses. Okay. So equal incremental cost criteria would dictate that each plant should carry half the total load. So if we say that both ICs are same for both the generators, then both generators can have half on half of the load and they can manage that. But the load is closer to generator 1 and generator 2 has to transfer via a lossy transmission line. So while it is obvious that the case that the plant 1 should carry a greater share of the load demand, thereby reducing the transmission losses. So logically you will see, in order for reduce the transmission loss, plant 1 should provide more and plant 2 should provide the less amount of power. Now we will come to this. This is the optimal generator scheduling considering the transmission loss. So we'll start with the equations. This is a bit, it is similar to the previous equation of the cost minimization. It is just we are including the transmission loss part. Okay. So again we have the overall cost of generation as capital C. It is given by the sum of all the costs of individual generators. And then we have an equality constraint, but here if you go to the previous equality constraint where the transmission losses are not taken care, it is now you have an extra part PL. PL here is the total transmission loss. So the total generation minus the demand minus the transmission loss, that is equal to 0. It is a new equation now. So we have as we have found the Lagrangian. Do not get confused with the Lagrangian. It is just a way to minimize a function. We just need to know that Lagrangian, what it does is that we arrange, we have a function that we need to minimize, okay, and we have a another function that is a constraint to this function, that we cannot minimize to any particular value. There should be certain constraints in the function. So what we do is that we sum these two parameters. One is the function and other is the constraint with a constant called the Lagrangian multiplier. Okay, nothing or nothing more than that. Okay, and then we make it as a total function. Then we make it as a total function, as we say it as a Lagrangian L. Okay, now in order to find the maxima, we make the differential of the Lagrangian equal to 0. So we do not need to get in the theory of the Lagrangian, but this is the procedure of getting the maxima and the minima. Okay, so here what we need to minimize? We need to minimize cost. And what is the constraint? Constraint is sigma PGI minus PD minus PL is 0. So we put it in the Lagrangian form, the main function minus lambda of the constraint function, and then we get a differential. Now here something is assumed, that the loss in the transmission line is the function of all the real power generated. Okay, that is the assumption. Okay, and for the optimal power dispatch, we need to differentiate it. Okay, and differentiating, just we follow differential and we'll get this equation. So this equation, the denominator, previously there was no denominator. If you check for the other part, without the transmission loss, there was no denominator, only dC by dP was equal to lambda. Now there is the denominator, dC dP divided by 1 minus dPL by dPg. Okay, now that denominator is called the penalty factor, or the factor that is required in when you consider consider the transmission loss inside our new optimal scheduling procedure. So this dPL or del PL by del PG is referred to as the incremental transmission loss, ITL. So you need to remember a few terms. One is incremental cost, IC, incremental transmission loss, that is delta PL by delta PG. It is called incremental transmission loss, ITL. So we can say IC, or incremental cost, is equal to lambda into 1 minus ITL. So this equation is called the exact coordination equation. Previously it was only the coordination equation without the transmission loss. Now we include the transmission loss with the incremental transmission loss, ITL. It is called the exact coordination equation. One of the most important simple but approximate methods of expressing the transmission loss as a function of generated power is through B coefficients. This method is reasonably adequate for a treatment of loss coordination in economic scheduling of load between plants. The general form of the loss formula is derived, we'll be talking about that using the B coefficient. So need not bother. For what we have said, that the transmission loss is a function of power at different masses, that we have said previously. See, you see the assumed part, PL is a function of both PGI, PG2 to all the PGs, right? What happens is that When do you have a transmission loss? When power is transferred from one bus to the other. So you need to have a bus 1 and bus 2. Okay, so we form a B coefficient. You need not bother. B coefficient is the matrix that is formed, where the matrix, the one side it is one bus and the other side it is the other bus real power. So PL is nothing but double summation of PGM, BMN and PGN. So PGM is bus from one side and PGN is bus to the other side, and in between you have this B coefficient. So it tells you not all values of the B matrix, not all values of the B matrix are are actually numbers. Most of them will be 0, because if one bus is not connected to the other bus, B matrix element will be 0, just as your Y bus system. Okay, so PGM and PGN are real power generation as M and nth plant, and BMN is a loss coefficient which are constants under certain assumed operating condition. So PGs are in megawatt, and obviously BMN is in inverse of megawatt. So the total transmission loss is PG transpose B into PG. Remember that. This is the total transmission loss. Okay. This is the equation that we need to put during the transmission loss calculation. So PG is PG is a set of all the real power generation at different buses, and B is a square matrix considering the number of, it is the row and column is the number of buses. Okay, so the total system power loss will be, that is dPL by dPGI. What is that? Total system power loss, and it is said as incremental transmission loss, ITL. Okay, so how to find this ITL? We differentiate it. So if we differentiate it, we will have these terms. So we can say that it may be noted that it is that the above expression, the other terms independent of PGI, if you differentiate the other terms that are independent of PGI, will be 0 when we differentiate it, and at the end we will have dPL by delta PGI is nothing but summation of 2 Bij into PGJ. Okay, that means what is PGJ? All the buses other than PI. Okay, so if you assume a plant cost curve as a quadratic function that we have assumed previously, so we can say that the incremental cost for a particular plant as a straight line. Okay, now you substitute these values, this delta PL by delta PGI and DC by dPGI on the above equation, that is in the cost equation. Okay, you will get these set of values. Just go through these. Okay, you can I think you can solve it by yourself, where you can have the equation given the PGI as a fraction of two expressions. Okay, you just need to rearrange. So this is how you get the power at one generator, depending on the losses and the power at the other generators. Okay, now this is the algorithm for optimum generation scheduling. So we start by choosing lambda, then we assume a certain values of p. Then we solve for the iterative for different values of p, okay, by this method. Okay, now we calculate the total loss. Now if we check for any equality, whether that equality is matched or not. So if we start a lambda, then we find the power. The power is found by the previously we have found power previously from the lambda chart. Okay, then we after finding the power, we find the losses. The B coefficient should be known previously. Okay, we find the total losses, and then we see that whether this equality is matched or not. The equality, the power flow equality, that is summation of all the generation is minus PD minus PL should be 0. It should not be exactly 0 because we are doing an iterative method. If it is very close to a very small value, you can say it is close to a 0, we can stop our iteration. But most of the time when we assume lambda and PG, obviously they will not be exact. So we go on increasing and decreasing lambda till that value is reached. Okay, so this is the end of this lecture. Okay, thank you so much.